So how does this relate to confidence intervals? So we have the same curve here representing the distribution of sample means, and distances are still measured in units of standard error. For purposes of teaching this and understanding it, I think it makes the most sense if instead of considering this line to be the population mean mu, let's call this the sample mean. So this is what we observed, 167 megatons CO2. Now this is what we observed for that particular sample, knowing full well that if we took another sample, it would probably not be 167. And if we took another sample after that, it's probably yet a different number. So here's the sample that we observed. This is our best estimate of the population mean, the one sample that we took. But we're going to assume, and it's a good assumption, that the sample means will be distributed about that, and that the sample means will be distributed according to a t distribution, or maybe a normal distribution. Having done this, we're going to follow the same kind of logic and same approach concerning, in particular, critical values that we did before. So we will switch pen colors, and ultimately we want to be able to define cutoffs and say if the value that we want to consider, for instance, a population mean, is unlikely to occur, then that means the value is going to have fallen in this rejection region, or maybe it falls in this rejection region. So we're, again, effectively saying that the value we are considering, such as the population mean, is significantly different than what we actually observed. And we will call something significantly different if there is a small probability of observing it, given the sample mean that we actually saw. So we know that these thresholds that define our rejection regions are the critical values. So that is the way they were defined earlier when we compared critical values to t-scores. The same concept applies for confidence intervals. We still have critical values defining rejection regions. Now, the thing about confidence intervals is the confidence interval is the distance between the two critical values. So we have a lower bound, which is represented by the lower critical value, and we have an upper bound that is represented by the higher, the positive critical value, with the mean being in the middle. So the confidence interval is two numbers. I've been representing that, let's get it out of the way there, as an open parenthesis, the lower bound, comma, a upper bound, extra one. So it's not just one number, it's two numbers. The confidence interval is not the magnitude of the critical value. So this represents where they are, but the confidence interval has to be in the units of the sample mean. So the mean was 106 megatons of CO2. So our confidence interval also, our lower bound and upper bound, needs to be megatons CO2. So it's going to be somewhere kind of around 167. Now, if you remember previously our critical values, this was like minus 2.3, and this was positive 2.3. So that just kind of demonstrates, one, that I cannot draw with a mouse, but two, that the confidence interval is not in critical value units. So we have to somehow convert this this minus 2.3, this positive 2.3, into the original units. And so we do that using the standard error. So remember that the critical value is the number of standard errors that we have to move away from the mean in order to produce this probability. So if the critical value is the number of standard errors away, then by looking at the equation, we can see we multiply by the standard error, and that will convert our 2.3, or 2.3 over here, into the original units and get an actual confidence interval. So we take the mean and we add the critical value, so the number of standard errors we had to move to get into our rejection region, and then convert that to original units by multiplying by the standard error. So that gives us effectively confidence values in original units. And so our interpretation as far as hypothesis test goes works the same way as critical values versus t-scores. So the t-score told us how many standard errors away our sample mean, our data needed to be, and if our t-score fell in a rejection region, then we rejected the null hypothesis. Well, the same thing goes with any other value. So in this case, maybe the population mean. And we can see whether or not our population mean falls within the do not reject region or in the rejection region. Since our confidence interval is in normal data units, we can directly look at the population mean in normal data units. So I think the population mean for question number 7 is 211. So if 211 fell there, then that's in the do not reject region. So we do not reject the null hypothesis. And conversely, if a population mean of 211 fell here, that is within our rejection region, meaning it is a value that is more extreme than the upper bound of our confidence interval. It's in the rejection region, so we reject the null hypothesis. The same thing would go if our population mean fell in our rejection region on the left-hand side. Again, just kind of highlighting that confidence intervals can only be done when comparing means and on two-tailed tests. And I think that does it.